Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into a problem that's all about maximizing potential, kind of like, figuring out the best way to arrange your day for peak productivity. You know what I mean?
Yeah, definitely.
Yeah.
And it's like one of those things where you're like,
Yeah.
got to get the most out of it.
Got optimized.
Totally.
So it's called Partition Array for maximum sum, and it's a real brain teaser.
It is. It is. It's a good one.
I think our listeners are going to enjoy this one.
What's really cool about it is how it blends array manipulation with optimization.
Okay.
You're given an array, basically a list of numbers, and you need to split it up into smaller chunks or subarrays.
Okay, so we're chopping up our list of numbers
Yeah, you guys.
into like bite-sized pieces.
Bite-sized pieces, yeah.
What makes this an optimization problem, though?
Well, once you've divided the array, every number within each subarray gets replaced by the biggest number in that chunk. Your mission? To figure out the way to divide the array that gives you the absolute largest total sum across all the chunks.
So if I have an array like 2, 1, 5, 4, 3, and my k value is 2, I might split into 2, 1, 5, 4, 3.
Right.
Then I'd replace each number with the max of its subarray, getting 2, 2, 5, 5, 3.
Yep.
And the goal is to find the split that gives me the biggest possible sum when I add all those numbers up.
You got it. Now imagine you're a project manager, and each number in the array represents the potential value of a task.
Okay.
You can only group tasks together in chunks of size k because of resource limits or deadlines. Your job is to find the task grouping that maximizes the overall project value.
Okay, that's a great analogy. I can see how this problem could have real-world applications.
Sure.
But before we get too far ahead of ourselves, let's think about how to actually solve this.
Right.
Where do we even begin?
So the most straightforward approach, though not the most efficient, is called brute force. Essentially, we'd try every single possible way to divide the array into subarrays, calculate the sum for each one, and pick the way with the highest sum.
That sounds incredibly tedious, especially if the array is large. Wouldn't we end up with a ridiculous number of combinations to check?
You're right. Brute force quickly becomes impractical as the array size grows. It's like trying to find the best route by exploring every single road in a city, even the dead ends.
There has to be a smarter way, right? Some way to avoid all that wasted effort.
Absolutely. That's where dynamic programming comes in.
Oh, nice.
It's a technique where we break a complex problem, like this one, into smaller overlapping subproblems and solve them in a way that avoids redundant calculations.
So instead of blindly trying every combination, we're finding a way to reuse our work and build upon previous solutions. Kind of like building a house brick by brick. We don't start from the roof.
Precisely. It's all about finding efficient ways to build up to the optimal solution. Dynamic programming is a powerful tool for this type of problem, and we'll explore two different approaches, top-down and bottom-up.
Okay, I'm intrigued. But before we dive into those, let's take a closer look at this brute force method.
Yeah.
Just to understand why it's not the best way to go.
Sure.
I think it would help illustrate the need for a more clever approach.
That's a good point. Let's say our array is 1, 4, 2, 3, and our k value is 2.
Okay.
With brute force, we'd have to check every possible way to split this array into chunks of size 2 or less.
So we'd have 1, 4, 2, 3.
Right.
Then 1, 4, 2, 3, and so on. It seems like the possibilities would multiply quickly as the array gets longer.
Exactly. For an array of length n, the number of possible partitions grows exponentially.
Oh, wow.
This means the time it takes to check all of them explodes as n increases, making it impractical for larger arrays.
Okay, all right, I'm convinced. Brute force is definitely not the way to go here.
That's a no-go.
So how does dynamic programming help us tackle this problem more efficiently?
So dynamic programming, it allows us to solve this by breaking it down into smaller overlapping subproblems.
Okay.
And we build up our solutions step by step. Think of it like building a bridge. You start with the smaller individual pieces.
Okay.
And you connect them to create a larger, more complex structure.
Okay, that makes sense. But how do we actually apply this to the partition array for maximum sum problem?
Right.
It still seems a bit abstract.
Sure. So let's start with the top-down approach,
Okay.
also known as memorization.
Memorization, okay.
The key here is to avoid redundant calculations.
Okay.
We'll use an array, let's call it DP, to store the results of our calculations as we go.
So DP is like our toolbox.
Yeah.
We're to fill it with the best possible sums we found
Exactly.
for different parts of the array.
Exactly. Each entry in our DP array will correspond to a starting point in the original array.
Yeah.
And it will store the maximum sum we can achieve starting from that index.
Okay, I'm visualizing this DP array in my mind. How do we start filling it up?
So we'll use a recursive function.
Okay.
Let's call it maxim. This function will take the original array, the maximum subarray size k, our DP array, and the current starting index as input.
So maxim knows where to start in the array, how big the chunks can be.
Right.
And it has our DP toolbox to check for pre-calculated solutions.
Exactly.
What happens next?
The first thing maxim does is check if we've already calculated the maximum sum for the current starting index.
Okay.
If we have, we simply return that value from our DP array, saving ourselves a lot of computation.
That's pretty clever. It's like checking our toolbox before we start building something from scratch.
Exactly.
What if we haven't calculated it yet?
That's where the recursion comes in.
Okay.
If the solution isn't in our DP array, we need to calculate it.
Great.
To do this, we'll explore all possible subarray lengths from 1 up to k, starting at our current index.
Okay, so we're trying out different chunk sizes
Yes.
to see which one gives us the best result.
Exactly.
What happens for each chunk is...
For each chunk size, we find the maximum element within that chunk.
Okay.
The biggest value in that little section of the array. Then we calculate the sum for that chunk, which is simply the maximum element multiplied by the length of the chunk.
So we're essentially simulating what would happen if we replaced all the values in that chunk with the maximum value.
Exactly. Then we make a recursive call to our maxim function, but this time with the starting index shifted to the end of the current chunk.
So we're saying, okay, assuming we choose this chunk,
Right.
what's the best possible sum we can get from the rest of the array?
Precisely. We do this for every possible chunk size, from 1 to k. For each size, we calculate the total sum by adding the sum of the current chunk to the maximum sum returned by the recursive call.
It's like we're trying all possible chunk sizes and recursively optimizing the remaining part of the array for each choice.
You got it. Finally, we pick the biggest sum out of all the options we explored.
Okay.
That's the maximum sum achievable starting from our original starting index. We store this value in our DP array so we don't have to recalculate it later,
Right.
and then we return it.
That's quite a process.
It is.
But I think I'm starting to see the elegance of it.
Yeah.
We're systematically exploring all possibilities, using recursion to optimize for each choice, and storing the best sums along the way. What are some potential pitfalls of this approach?
Well, as elegant as memorization is, one thing to watch out for is stack overflow errors.
Okay.
If our array is very large and we have deep recursion, we could end up with a stack overflow.
So we have to be mindful of the recursion depth.
Exactly.
That makes sense. Now, I'm curious about the bottom-up approach.
Yeah.
How does that one work? And does it avoid this stack overflow issue?
The bottom-up approach takes a different strategy.
Okay.
Instead of breaking the problem down recursively, it builds a solution up from the ground up.
Okay.
It still uses our DP array,
Okay.
but we fill it in a different order.
Interesting. So it's less about exploring possibilities and more about systematically constructing the best solution.
You could say that. Let's walk through it.
Okay, I'm ready. How do we get started with this bottom-up method?
With the bottom-up approach, we start by initializing the last element of our DP array to 0.
Okay.
This makes sense because if we're at the very end of the array, there's nothing left to sum up.
So it's like saying the best possible sum we can get from an empty subarray is 0.
Right.
That's
Yeah.
our starting point.
Exactly. Now we move to the second to last element of the array and work our way backwards, one element at a time.
Okay, so we're moving from right to left through the array.
Correct.
What do we do for each element?
For each element, we consider all possible subarrays that can end at that element.
Okay.
Remember, the subarray length can be anywhere from 1 to k.
So for each element, we're trying out different chunk sizes, just like the top-down approach.
Exactly.
What happens next?
For each possible chunk size, we find the maximum element within that chunk and multiply it by the chunk's length to get the sum for that chunk.
Right, so we're finding the best possible sum for that chunk, assuming we replace all its values with the maximum one.
Now here's the key difference from the top-down approach.
Okay.
Instead of making recursive calls, we look ahead in our DP array.
Okay.
We add the chunk's sum to the value stored in the DP array at the index immediately following the end of the current chunk.
Why are we looking ahead in the DP array?
Because we've already calculated the best possible sum for everything, starting from that point onward.
Oh.
Remember, we're working backwards through the array.
Ah, I see. We're combining the current chunk sum with the best possible sum for the rest of the array,
Right.
which we've already figured out.
Precisely. We repeat this for every possible chunk size ending at the current element, keeping track of the largest total sum we find.
Okay.
That largest sum becomes the new value in our DP array for the current element's index.
So we're systematically building up our solution by using previously calculated results, kind of like laying bricks to build a wall.
Exactly. And we continue this process until we reach the beginning of the array.
Cool.
At that point, the first element of the DP array will hold the maximum sum for the entire array.
Wow, that's a really clever way to avoid recursion. But how does this bottom-up approach compare to the top-down method in terms of efficiency?
Both approaches have a time complexity of onk, where n is the length of the array and k is the maximum subarray size.
Okay.
This means the time it takes to solve the problem grows linearly with both the size of the array and the maximum chunk size.
Okay, so the time complexity is the same. What about space complexity? How much memory do these approaches use?
Both approaches use on space because of the DP array,
Okay.
but there's a potential optimization for the bottom-up approach.
An optimization, tell me more.
Notice that in the bottom-up approach, we only ever need the values from k previous entries in the DP array to calculate the current entry.
You're right. We're only looking ahead a fixed distance of k elements.
So instead of using a full DP array of size n, we could use a circular buffer of size k to store only the necessary values.
Okay.
This reduces the space complexity to OK,
Wow.
which can be a significant saving if k is much smaller than n.
That's a really neat trick. So we have two approaches, both with the same time complexity, but with the bottom-up approach potentially using less memory.
Right.
How do we decide which one to use in practice?
It often comes down to the specific constraints of the problem and your personal coding style.
Yeah.
Top-down memorization can be more intuitive if you're comfortable with recursion,
Okay.
but bottom-up is generally faster and avoids the risk of stack overflow.
So if we're worried about stack overflow or need to be very efficient with memory, bottom-up is the way to go.
Exactly.
But if the problem is relatively small and we value code readability, top-down might be a good choice.
Exactly. The important thing is to understand both approaches and choose the one that best fits your needs.
Well, this deep dive into the partition array for maximum sum problem has been incredibly insightful.
That's a good one.
We've explored the brute force approach, learned why it's not ideal, and then discovered the power of dynamic programming with both top-down and bottom-up methods.
And remember, dynamic programming is a versatile technique that can be applied to many other problems where you need to break down a complex task into smaller, overlapping subproblems.
Absolutely. Thanks for joining us on AI.Code.Cast. Be sure to check out the show notes for additional resources and coding challenges to practice what you've learned. And until next time, keep coding and keep exploring.